structures that we learn for states of matter. Okay, so we started with number 1. So maybe someone can help me. Number 1. So what are the structures that we have learned until now? So maybe Ryan, can you actually help us out over here?
Simple molecular.
Okay, simple molecular. So one of it, simple molecular. Thompson. Oh, Thompson just went to toilet. Wilson, can you actually tell me what else?
I'm here.
Okay, Thompson. Give me what else that you have learned under structure, different structure.
Then ionic lattice.
Ionic lattice. So it will be giant, yeah, giant ionic lattice. Okay, Wilson.
Giant covalent.
Okay. So it's not, I think when I was teaching, it's actually giant, not covalent, it's giant molecular. Okay, giant molecular, but it's actually the same meaning, yeah. Giant molecular structure. So number 4, okay, there are total 5, yeah. So number 4, Catherine. Simple what?
Simple atomic.
Yes, simple atomic. Okay, there's another one, giant. Okay, maybe Audrey, do you know this? Number 5.
Metallic.
Yes, so it's giant metallic lattice. So when I write this, okay, I do have 2 times, okay, the term lattice, okay, being written over here. Okay, so I just want to actually find out more, okay, on what is the meaning of lattice. So can someone actually help me about the meaning of lattice? Maybe we'll call Nicholas Chai. Okay, what do you understand by the term lattice, Nicholas Chai?
3D structure.
Again, not so clear.
3D structure.
3D structure. Okay, apart from 3D structure, okay, apart from the 3D structure, I think one point is really missing over there. This 3D structure, okay, has what?
Intramolecular bonds.
Okay, they do have bonds, okay, they do have bonds, but I think the bonds will actually, what is so special? I think when related to lattice, okay, even when you look at the simple molecular, under simple molecular, there is one time I actually mentioned that there's also simple molecular lattice as well. Okay, example, I2, water molecules, they are simple molecular lattice. So when we see lattice, lattice means, okay, 3D, but I think the important thing that you need to take note over here is lattice has a repeating arrangement. Okay, they repeat. Okay, that's the meaning of lattice. So if you actually look at the, like for example, giant molecular structure, okay, giant molecular structure like diamond is actually lattice. Okay, so you can actually say giant molecular lattice, still the same. Okay, lattice means it's a repeating arrangement. Okay, it's a repeating arrangement. So that is the meaning of lattice. Okay, so now coming back, okay, let's actually start from number 4. Okay, simple atomic. Okay, when it comes to simple atomic, can you actually give me some examples for simple atomic? Maybe Michelle V. What has simple atomic example?
I don't know, sir.
Noble gases. Okay,
Oh,
noble
right,
gases. Yeah. Okay, so noble gases, they have this simple atomic structure. So give us some example, maybe 3 examples for noble gases. Michelle V, just give us 3 examples.
Helium.
Okay.
Argon.
Okay.
Neon.
Neon. Okay. So out of this, okay, the example that you have given, okay, I think it's good you actually mentioned about helium and neon. Yeah, helium and neon. Helium and neon, they are kind of most of the time they are referred as ideal gas. Okay, they are referred like closely representing ideal gas. So if I actually ask you why they actually refer helium and neon closely representing ideal gas, Frederick, can you actually explain why helium and neon, they are always being represented as a very ideal?
Because they're a simple atomic.
Yes, they have simple atomic, but please go deeper about the assumptions that is made for ideal gas. So what you should say, in order
They
to
are
be an
noble
ideal
gases.
gas, yeah, in order to be ideal gas, what you need to have, know what?
What's it called? No pairs or intermolecular forces.
Okay, no intermolecular forces. In this case, what is the forces of attraction between helium atoms and neon atoms?
Helium gas, sir.
Yeah, helium gas and neon. Okay,
Van der
so
Waals.
yeah, they only have van der Waals forces of attraction, but these van der Waals forces of attraction, if you look at helium, helium is going to be 2 4. Okay, neon is going to be, I think 10, maybe 20 over there, I'm not sure. Okay, but again, you see there are 2 electrons and only 10 electrons in neon. It means the van der Waals forces depends on the number of electrons. Okay, you can see that the number of electrons for helium, they're quite less. So it means the van der Waals forces that they have is quite low. So that explains, okay, why helium and neon can behave as an ideal gas. And also, you can also see that because they are having less number of electrons, okay, the volume is considered to be small, because according to the definition for ideal gas, they say the negligible volume of the particle. Okay, so in this case, they satisfy, okay, they satisfy the term of ideal gas. So therefore, okay, helium and neon, we categorize them under simple atomic. Okay, roughly that's going to be about simple atomic. Now, let's actually move on to the simple molecular, okay, simple molecular structure. So what can you say about simple molecular structure? Maybe let's actually start with example, okay, example. But before we go for the example, before I forget, maybe we can start about the definition of molecule. Sharon, can you tell us about what do you understand about molecule?
It's a group of atoms
Yes.
bonded together.
Yes. So it's a group of atoms bonded together. Okay, it's a group of atoms bonded together. So it can be same atom. Okay, it can be same atom, or it can be different atoms as well. Okay, so if you're talking about different atom, Josh, can you give me 2 examples of different atoms bonded?
Oxygen and carbon.
Okay. What do you mean oxygen and carbon? It means carbon dioxide, you mean? Are you talking about
O2.
CO2? I think CO2 is a simple molecule.
Yeah.
So CO2 is one simple molecule. I think even O2, okay, the one that you
Yeah,
mentioned,
O2.
yeah, that is also a simple molecule as well. So how about having the same atoms bonded together? So can we actually have 2 examples related to that? Megan, can you actually recall the one that I gave you during the lesson? Simple molecular. Something related with P and something related with sulfur.
P4 and S8.
Yeah, P4 and S8. Please take note. Okay, they do exist, okay, in form of molecule. Okay, the solid phosphorus is always P4. Solid sulfur is always S8. Okay, so this one is simple molecular. Now, I mentioned also just now, okay, there is one part that I mentioned about simple molecular lattice. Okay, there is also simple molecular lattice, where there is going to be something like a repeating arrangement. Okay, so I have actually given 3 examples for the simple molecular lattice. Okay, so what are the 3 examples that I given? Maybe let's actually ask Jasmine. Can you remember that?
Iodine.
Iodine, okay, is one of them. Okay, iodine. How about, okay, Jeffrey, can you give us another 2? I think both of them are related.
Chlorine.
No? Lattice, chlorine don't actually form lattice. Something to do with H2O. So it can be water molecules or H2O in form of ice. Okay, both of them, okay, they can actually form lattice. Okay, the lattice that we are talking about will be more like a tetrahedral structure. Okay, please actually go and look for this. And also, okay, I have added, apart from all these example, okay, there are 2 more, okay, structures that also have simple molecular structure, which is electrode of carbon. Okay, so talking about electrode of carbon, okay, what is meant by the term electrode? Okay, electrode. So maybe let's actually select Michael. What do you understand about the term electrode? What is electrode?
I'm not sure.
You're not sure. It's okay. If you're not sure, we can actually ask someone. Owen, you can go. Elizabeth, what do you understand about electrode?
They have different physical form.
Yes, so it means same element. Okay, same element but different form. Okay, same element forming different structure.
Sir,
Yeah.
how do you know if compound is simple molecular or giant lattice?
Okay, how do we know? Okay, because now we are learning the structure. Okay, so for now, okay, just follow the examples given. Yeah, for now you just follow. Okay, but for example, you can guess whether they are actually simple or not. Okay, but these are the general guess. Like for example, if let's say here, okay, I didn't discuss. Of course, there's so many molecules around. Okay, we don't have the time to discuss everything. But this is going to be a guide. This example will be serve as a guide for us to come to, like for example, conclusion. What might be the shape? Okay, like for example, if simple molecular lattice, yes, they already mentioned these are the lattices, right? But if I have nitrogen gas, okay, nitrogen gas didn't come under simple molecular lattice. So N2, okay, most likely they will have simple molecular form. So that is how you actually find out. Okay, so that is going to be like for example, later on you will learn about giant structures. Like for example, giant metallic lattice. I think all metals, they actually form metallic lattice. Okay, giant covalent. Okay, giant molecular. There is you will learn later. Okay, there are diamond, graphite. So there are some structures that you will learn. So we will actually use this as a guide to reach whether this is going to be what structure. Okay, so generally ionic forms. Okay, like for example, MgCl2, for example, yeah, they do form giant ionic lattice. All ionic compounds, they have high melting point and boiling point because they can form giant ionic lattice. So you can actually use it as a way to remember, okay, or the way to actually come into conclusion what kind of a structure that they have. Okay, so anyway, does it answer your question, Christopher?
Yeah.
Yeah.
So
So
then
here,
simple molecular is usually
hmm,
covalent then. If
yeah,
giant
simple molecular, they are covalent. Okay, simple molecular, they are always covalent. The moment they are ionic, they will have giant ionic. So electrode, okay, under electrode, yeah. So there are 2 electrodes of carbon. Okay, there are 2 electrodes of carbon that I told you will have simple molecular. Okay, so what are the 2 electrodes of carbon that have simple molecular? See whether you remember this, Nathan. Did you write it somewhere? Simple molecular. 2 electrodes of carbon that have simple molecular structure. Write it somewhere next time, yeah? So this one is going to be fullerene. Okay, fullerene, and this one is going to be nanotube. Or to be exact, okay, to be exact, both of them, they are fullerene. Okay, both of them, they are fullerene. Okay, so to be exact, if I erase this, okay, I think better to actually say both of them are fullerene. And fullerene has 2 forms, Buckminster. We will learn about this today. Okay, Buckminster fullerene, and this one is going to be nanotube. Okay, these are going to be the one of the example here. But apart from this, okay, when I put it apart aside, okay, so electrodes, okay, electrodes of carbon. Okay, electrodes of carbon, they can exist in total of 4 ways. Okay, one of it is going to be diamond. Second is going to be graphite. Third is going to be graphene. And then the last is fullerene. And fullerenes, okay, they do exist in 2 forms, like what I wrote just now. Okay, so it's Buckminster fullerene, or they actually simplify by saying buckyball. Okay, buckyball. Okay, and this one is nanotube. Okay, so coming back here, okay, we go for the another one, which is going to be giant ionic lattices. Okay, for giant ionic lattice, okay, we have learned they have cubic structure in our syllabus, which is going to be NaCl and MgO. Okay, so these are the one that is inside our syllabus, and I have actually shown you, okay, the diagram when it comes to the cube of NaCl. What do you need to know is each one Na plus, okay, is bonded to how many Cl minus. Each one Cl minus is bonded to how many Na plus. So this is important for this part, yeah. So this one, Wilson, can you actually tell me how many Cl minus? Each one ion, 6. Okay, the same applies for this. Okay, so please take note of this. Okay, so there are each sodium ion, okay, they are bonded to 6 chloride ions, and each chloride ions, they are bonded to 6 sodium ions. Okay, so it's not actually reflected over there, okay, on the screen. Okay, maybe it's laggy or something like that. But anyway, okay, that is going to be giant ionic lattice. Okay, giant ionic lattice, you are going to have that situation. But talking, if you go and explore further, okay, about giant ionic lattices, what else that you can say? Okay, what else that we can say about giant ionic lattice? I think most we can talk about the properties of giant ionic lattices. Okay, so let's actually come up with the properties of that. So maybe Giuliano, can you give me the properties of giant ionic lattices?
High melting point and boiling point.
Okay, good. Okay, high melting point and boiling point. Okay,
Soluble
because,
in
yeah,
soluble in water.
soluble in water because they can actually form what bond?
The ionic one
No.
with the ion dipole bond.
Yes, they will form ion dipole bond. Okay, so number 3. Okay, if you go to the toilet, just write in the chat and then go. Yeah, later I'll check. Okay, what else?
They only conduct electricity when they in aqueous or molten.
Yes, okay, either in aqueous or molten. Why is that?
Because when solid, no electron or ion can move freely.
Not electron, you must actually mention about no free moving ion.
Oh,
Okay,
okay.
don't mention about electron. Yeah, no free moving ion. Yeah, so these are the points. Okay, high melting point, soluble in water, conduct electricity. I think when it comes to very important point, okay, let's say there's going to be some kind of forces of impact. For example, okay, Kevin, what can you say if let's say there is some kind of forces of impact and it happened to slide on top of each other? What happened to that structure, Kevin?
It becomes brittle.
Yes. Okay, they will break because okay the arrangement okay of those ions okay will be disrupted, and then if let's say you have the same charges, they start to repel from each other, so they will break. Okay, so that is going to be brittle. So this is the part of the ionic lattice, giant ionic lattice. And then here okay we go for the giant metallic lattice now. Okay, all metals they have this giant metallic lattice. Okay, but when we say metallic bond, okay, metallic bond, or what do we refer? Is the bonding between metal and metal atoms or something else? Given, can you tell metallic bond is from what and what?
Between the ion and the delocalized C of.
Yes, it's between the metal ion and C of delocalized electron. Okay, C of delocalized electron. Now, when the bonding about C metal ion and C of delocalized electron, what can you say about that bond? Is it acting at a single direction or is it acting at all directions? Owen?
All directions.
Yeah, it acts at all directions. Therefore, okay, when you have okay, forces of impact, okay, let's actually go for the property. When there is a forces of impact, okay, and let's say the giant metallic lattice, the layer happen to slide on top of each other, okay, will they be brittle, Owen?
Yeah.
No.
No, sorry.
They are not going to be broken because okay, not brittle, okay, because the metallic bond acts at all directions. Okay, new bonds okay can be easily formed. Okay, when you have new bonds can be easily formed, okay, this will give rise to two important property. Okay, what are the two important property because new bonds can be formed? Okay, so this one maybe I'll ask Benedict. What are the two important property when you have ability to slide and then new bonds can be formed? So what are the two properties that you can say because of this this I think special characteristic? Metals are start with M, start with D.
Ductile and malleable.
Yes, okay, so metals are malleable, okay, and metals are ductile, okay. So malleable, can you explain, Benedict? Can be hammered into different shapes.
It can be changed.
And ductile?
Can be stretched like turtle wire.
Yeah. So can be elongated, okay, without breaking. Okay, can be elongated to form long wires, okay. So this one is going to be some of the properties of this metallic lattice. One of it, okay, you see, not brittle, they are hard, okay, they are malleable, they are ductile. Okay, what else that you can say? Can they conduct electricity and heat well, Giuliano?
Yes.
Yeah, so they can conduct electricity and they can actually conduct the heat. Okay, so ability to conduct the electricity now, Giuliano, is it because of C of delocalized electron or free moving ions? This is very important.
The C of delocalized electron.
Yes, okay, please be very careful. Yeah, so C of delocalized electrons, okay, they will actually help, okay, in conducting the electricity. But when it comes to ionic structures, okay, the free moving ions will be the one that is going to help to conduct electricity. So there are going to be difference over here. And do remember, metals, they have high boiling point and they have high melting point as well. I think this one is some of it, okay, the properties that you need to remember. Okay, so what we are going to do today, okay, is going to be about the giant molecular structure. So related to this giant molecular structure, okay, before we go into detail, I'll just give you an overview. Yeah. So the giant molecular structure that we are going to look at is going to be more towards a covalent structure, more towards the electrode of carbon. So one of it that we are going to look into detail is going to be diamond. Okay. And then number 2, we are going to look into graphite. Number 3, okay, is going to be graphene. Number 4 is going to be silicon 4 oxide. So which is going to be SiO2, which is actually one of the common thing that is found in the sand. So they can be used to make glass. Okay, so this one, diamond, graphite, graphene, okay, and then silicon 4 oxide. Okay, these are the one that we will look into under the giant molecular structure. But okay, I think we have done little bit on diamond, we have done on graphite. So let's actually go and revise on diamond, the structure of diamond, and then let's actually revise on the structure of graphite as well before we go into graphene and SiO2. Yeah. Okay, so what can you actually say about, let's say if we want to compare both of them. Okay, if I want to compare diamond and graphite, so how do I compare? Okay, so maybe we'll ask Arwen. Arwen, can you actually give me a point so that if I want to compare, how do I compare diamond and graphite?
Graphite can that
Graphite can?
the molecule like slide.
Okay, so graphite have, rather than saying molecule can slide, okay, graphite, they are arranged in form of layers. Okay, okay, so there are no layers over here. Okay, they are arranged in form of layers, and these layers, they can slide. Okay, so if they are sliding, okay, what can you say about graphite? Okay, even can you tell me if there is layers of this graphite, they are sliding on top of each other, it will give rise to one important property that is important when it comes to its use, which is as lubricants. Okay, so what is the important property? Starts with S.
I'm not sure, sir.
Still not sure?
Slippery?
Yes, slippery. Okay, slippery. Okay, that able, the layers able to slide. Okay, that will actually give you the ability, okay, which is going to be slippery. Okay, so it's kind of a soft. Okay, so they will be used as lubricants. Okay, and then graphite, I think what else I can compare, maybe graphite is actually black. Okay, generally diamond are white. Okay, but they are more different colors, you can see from my video. Yeah, the one that I've done previously. But anyway, okay, so if we actually try to compare, what else you can compare? Elizabeth, let's talk about one carbon is bonded to how many carbon? One carbon bonded to how many carbon?
3.
Okay, for this is 3, for this one is going to be 4. Okay, So it means that for each one carbon, there is one electron. Okay, there is no extra electron. Okay, there's no extra electron. So when it comes to, like, let's say this one is slippery, this one I'll just put it as hard. Yeah, hard. Okay, because of the structure. So when it's hard, I think the structure is going to be arranged in a tetrahedral repeating form. Yeah, tetrahedral form. No layers, okay, and so on. I think if we move on, okay, because of this presence of this electron for graphite, okay, what can you say about the ability to conduct electricity? So Owen, can graphite conduct electricity?
Graphite can, diamond cannot.
Yeah, can conduct electricity. This one cannot conduct electricity. Okay, so next, what else? Is there anything else you want to add? Diamond and graphite, layers, slide, hard. Okay, I think let's actually compare the boiling point and melting point. Both of them, melting point and boiling point, they are high. Okay, melting point and boiling point is high. Okay, but which one is higher, diamond or graphite? Michael?
Diamond.
Okay, diamond is higher. Okay, why? Why is lower for graphite?
More carbon bonds. More bonds.
Weak van der Waals forces between what? Please actually revise on this, okay? Because of the weak van der Waals forces between the layers, because if you have one single layer, okay, each layer, I think they have bonded with 3 carbon atoms via covalent structure, okay, covalent structure. So they are quite strong, but between the layers, okay, it's weak, and that actually makes it able to slide, and that also makes the melting point and boiling point to be slightly lower than diamond. Okay, another one that I can actually write down is going to be, because I mentioned about tetrahedral form. Okay, graphite, they are arranged in hexagonal shapes. Okay, the carbon that you have, okay, they are going to be arranged in hexagonal shape. So they are going to be repeating. Okay, something like this. Okay, so I think I couldn't recall. Okay, there might be more, okay, differences, but I think this will be the main differences between diamond and graphite. Okay, so please actually take note of this. So now, okay, I will actually go into silicon 4 oxide. I think I mentioned this to you also before. Okay, before we go into graphene, so I will also teach you about silicon 4 oxide. Silicon 4 oxide is actually when they ask you in exams, okay, they ask many times in MCQ questions, okay, level 1 questions, okay, like for example, you study and then you just got the info, you just go and write it down, yeah, in your test. Like for example, the common questions that they like to ask is going to be like, for example, if you have in silicon 4 oxide, if you have one atom of Si, okay, how many atoms of oxygen is bonded to this Si? So they will ask you about that. Okay, so if you have, like for example, one atom of oxygen, okay, one atom of oxygen, how many atoms are going to be attached to that, and so on. They will ask you about that. So let's actually recall back, okay, about that. Okay, so hold on, I'll just try to screencast again. Fail to start. Okay, anyway, okay, while we are actually here, okay, while my iPad comes into, okay, can connect again. So maybe Audrey, can you actually tell me, okay, each one Si, okay, will be bonded to how many oxygen? Audrey?
4.
Okay, do remember this. SiO2 is not actually just Si and then 2. Then you just give 2 over there. That's going to be wrong. So this one is going to be 1 atom of Si is bonded to 4 oxygen. And then each 1 atom of oxygen is going to be bonded to only 2 Si. Okay, this one memorize. Okay, how? Okay, I think this one I have actually shown you the structure. Okay, the structure of it. So if you look at the structure for SiO2, okay, this is going to be the structure of SiO2. You can see clearly that if this one, okay, this one is going to be, change the color. So if this one is oxygen, okay, so you can see oxygen, each oxygen is going to be bonded to how many O, how many Si? So you have 1 and you have 2. Okay, but if you are looking into each, for example, each Si is going to be bonded with how many oxygen, for example. So this is going to be Si. So you have 1, 2, 3, and then 4. Okay, so this one is actually from the diagram. Okay, if you look at the diagram, it's somehow similar to diamond. Okay, but they do not actually have a very compact structure like diamond. Okay, so that actually makes some sort of difference. Okay, but do remember when it comes to boiling point and melting point, okay, of SiO2, okay, the boiling point and melting point is quite high. Okay, because of this structure. Okay, because the giant structure, giant molecular structure. So that actually similar, you can actually just remember silicon peroxide is hard. Okay, they are very strong. Okay, boiling point, melting point is high. Okay, because of this. Okay, so now, okay, we will actually go into